All right, welcome back, everybody. Today we're doing section 14.3, which is all about partial derivatives. It's a pretty fun section. It's where we finally get to talk about doing derivatives in, I'll just say the X and Y directions. And it's going to set us up for stuff we're going to talk about later involving like the directional derivative, the gradient, and so on. Plus, we also get to touch on the concept of a partial differential equation today. So let's go ahead and get started. Pull up the slides. Oop, move this out of the way. There we go. Okay, so here's the overview. First, we're going to get some motivation for what these are and why we care about them. Then we're going to get the definition of a partial derivative. We will talk about a geometric interpretation. And then we're going to talk about notation, because there's actually a lot of different notations for partial derivatives. Then we'll talk about how to extend the notion to functions of several variables. We'll talk about higher partial derivatives. And then we'll finish off by talking a little bit about PDEs, partial differential equations. Okay, so here's the motivation. If you look back at everything we've talked about in the course so far, we've still only been talking about derivatives of single variable functions. The variable was usually t, right? But they were still single variable functions. What we want to do is we want to extend the notion of a derivative and differentiability to multivariable functions, functions of x and y, or x and y and z, or x1, x2, x3, dot, 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 all the way to xn. So let's start with some intuition first. If you remember with functions of a single variable, the derivative gave you the slope of the tangent line to a curve in space, right? Well, if you've got a function of two variables, let's say, then the object that it describes is actually a surface in space. And we kind of saw this a little bit already, right? So z equals f of xy is a surface, not just a line or a curve. So the issue is this: a tangent line to a surface is not a well-defined object outright. So if I give you a surface and I give you like a point on the surface and I say, what's the tangent line to the surface at that point? You can't give me a you can't give me a well-defined answer, because the tangent really could be going, the tangent line could be going in any direction, right? So this pencil here is like all the possible different tangent lines to a surface at a point. So you've got infinitely many choices. So a good place to start narrowing down the choices is to find the slope of the tangent line, the derivative, in the x and y directions. So that's what we're going to do first. How do we find the slope of the tangent line in the x direction or the y direction? So here's the definition. Given a function f of x comma y, we're going to fix the value y equals b, all right? Then what we can do is we can rewrite this two variable function as a single variable function, because we've held the second coordinate fixed. So now this is just a function of one variable. So g of x is f of x comma b. And then what we can do is we can take the derivative with respect to x. So the partial derivative with respect to x at this point is basically the derivative of this single variable function where you held y fixed. So we denote it like so. So f sub x of a comma b, that's just equal to g prime of a, where g of x is this function where we've held y fixed. So the basic idea is this right here. If we fix y at the point b, then we can explore the derivative of f with respect to x along the slice of the graph determined by b. We'll get a geometric interpretation in just a minute. But now we can just use the definition of a derivative that we remember from good old Calc 1, right? We just take the limit as h goes to 0 of the difference quotient. And using our notation of f, this is what it looks like. So this right here is the definition of the partial derivative with respect to x at the point a comma b. Notice here that the increment only occurs in terms of x, right? Because y is held fixed. Y is held fixed. So the increment is occurring in the x direction. Now, similarly, you could do the same thing with I'll just say with y. You could instead fix x to be equal to a, and then do the derivative with respect to y. And when you do that, you get this right here. So just in general, this is the partial derivative with respect to x, and this is the partial derivative with respect to y. And now you'll notice the increment is actually affecting the y coordinate here, not the x coordinate like it was a moment ago. Okay, so let's get a little bit of geometric intuition just so that we can see what's actually happening here. So what the partial derivatives describe is they're giving you the slopes of the tangent lines to the surface z equals f of x, y at the point a comma b in the x and y directions. So if you look at this picture right here, this is a pretty good picture of what's happening. The surface S is this kind of curvy surface you see here. Here's the point a comma b comma c. C is what you get when you plug in a comma b to your function. And then we're basically, how do I put it? It's like we're slicing the surface with a plane. In this case, it would be the plane denoted by y equals b. And then when we slice our surface with a plane like so, we get a space curve. Let me let that fade away. We get a space curve right here. Now that we have a space curve, we can find a tangent line to the curve at that point, and that's exactly what T1 is right here. So T1 is basically the tangent line in the x direction, and the slope of that tangent line is f sub x. Oops, come here. F sub x at a comma b is the slope of T1, just like so. Similarly, you can do the same thing with a plane and slice the surface this way. It's going to look a little worse, I apologize. Maybe like this, and you'll get another space curve there, and then you can find the tangent line to that point again, and that's what this is, T2. So what is f sub y? F sub y of a comma b is the slope of T2 right here. So that's basically the idea. So anytime you think of a partial derivative with respect to x, you should be thinking about the derivative in the x direction, or if the partial derivative with respect to y is the derivative in the y direction. That's the easiest way to think of it. Yeah, so just try to keep that in mind when you're doing these things. Now we got to talk a little bit about notation. So there are many, many notations for partial derivatives. And what's really important is this. What's really important is that the variable of differentiation is made clear in some way. So this is where Lagrange's notation that you learned back in Calc 1, the prime notation really is just not sufficient anymore. It's not sufficient anymore because that prime does not indicate which direction you're taking the derivative in any way, right? And we have options here. We have infinitely many options, actually. So whatever notation we use has to indicate the variable of differentiation in some way. So this is why when I teach Calculus 1, I actually try to emphasize Leibniz's notation, because Leibniz's notation actually tells you the variable of differentiation. And when you've got a whole bunch of variables flying around and you've got a whole bunch of different kinds of derivatives, you need some way of specifying which one you're even talking about. So a common symbol, well, I'll just say this. So a common symbol to indicate a partial derivative is this one right here. Let me zoom in a little bit so you can see it. There you go. The way that I write it is I kind of do this. It takes practice to get used to writing a new mathematical symbol, but it's slightly different from the capital or the lowercase d notation, because d is usually what we use when we want to indicate, or when there's only one possible variable. So if you look back in your Calculus 1 notes or anything, you'll see that you were just using d, d, d. Well, this one is partial, and people will actually say that. They'll say, oh, partial x, partial y, partial z, partial blah, blah, blah. So that's what that little symbol means. It means partial derivative. Actually, you know what? Sometimes it'll also be used to indicate the boundary of an object. We'll see that later on in the end of the course, like chapter 16. But that's a common symbol for partial derivatives. Here are some other symbols you can use. There's a whole bunch here. And just like I talked about in Calc 1, remember that the active differentiation is an operation. So we call this thing, or I should say, we call this thing right here, the partial differential operator. It's a function, and you put functions into it, and it spits out the derivative in that direction. That's what it spits out. So these are all equivalent notations. Let me just go through it. F sub x, partial f, partial x, um, partial, I'll just say this is a partial x of f. Can also use this notation. F1 is also used commonly just to indicate that it's like the derivative with respect to the first component. D1 of f, dx of f, these are all congruent, what am I saying? These are all equivalent notations. That's really what it means. Same thing down here. Same thing down here. Okay. Now, here's the big idea. So, how do you actually compute these things? Now that we know what they are, slopes in the x and y direction, slopes of the tangent lines, how do you actually compute one? And even though this may seem complicated at first, it's actually very simple and straightforward. If you want to actually compute a partial derivative, hold one variable fixed. That means treat it as a constant and differentiate with respect to the other variable. So if you want to do the derivative with respect to x, you just pretend that y is a constant and it behaves like a constant with respect to that differential operator. So it will be just like a constant, just like you did back in Calc 1. So let's try this example. This one, let me see. This one I'm going to do first. If you want to work on it along with me, go for it. But then I'll let you try the next one on your own the first time. But let me do this one together first. So here's our function f of x comma y, and we're just going to compute the partial with respect to x and the partial with respect to y, and we're going to evaluate them at the point 2 comma 1. So just like I said a moment ago, all you really do is to compute this, treat y as a constant and x as the variable. So here's what we've got. F sub x of x comma y is the partial with respect to x of that function. X is the only variable in this process here. Y is a constant. So what we're going to do is we're going to differentiate our function, but only x is, we're only going to treat x as a variable. Y, anything involving a y is going to hold, we're going to hold it like a constant. So what is the derivative of this with respect to x? It's 8x cubed. What is the derivative of this with respect to x? Well, you've got a constant 3 and you've got a constant y squared. The only thing that is going to have the power rule applied to it is x cubed, which will become 3x squared. So you're going to get 9x squared times y squared, which is right here. Then we're going to differentiate this last term with respect to x. And if we differentiate it with respect to x, then it's going to disappear. It's going to become 0, right? Because here, this doesn't have any x's in it. So to this differential operator, it treats this as a constant. Derivative of a constant is 0, and we're done. Right. Now that we have the general formula, so what does this formula actually give us? This gives you the slope of the tangent line in the x direction at any point on the surface, f of x comma y. So what do we want to do? We want to see what is the slope of the tangent line in the x direction on this surface at the point 2 comma 1. So now we just evaluate this partial derivative at 2 comma 1, and we get 100. And that's it. So if you think back to this picture, right here, think back to this picture, what we just found out is that the slope of this line right here is 100. That's basically it. Okay, back to this. Okay, now let's do the partial in the direction of, in the y direction. So here we go. Same idea, except now we're going to treat x as a constant, and y is the thing that's going to change. So in this function, everything, well, I won't say everything, just pretend that x is a constant. So the only thing we're going to apply the power rule to are these. So if we differentiate this with respect to y, it's 0, gone. If we differentiate this with respect to y, this is a constant, this becomes 2y, so we get 6x cubed y. And then here, power rule, straight up power rule, you get negative 12y to the fifth. And this right here is the formula for the slope in the y direction at any point on the surface. Now we evaluate that function at 2 comma 1, and we get 36, just like so. Cool stuff. Okay, so before we go to the next example, what I want to do is I want to show you how to do this in Mathematica as well. Again, Mathematica can do derivatives, it can do partial derivatives, it can do higher order derivatives, it can do a lot. So if you ever want to check your work, or if you want, funny enough, when I was checking over my slides, I used Mathematica to verify a couple of these, and I realized I had made a typo on a couple of the examples, so I'm glad I did. But let me show you how to do it in Mathematica. Here's the first thing I did. So here's the function that we saw. You can see that, right? Yeah. Here's the function that we saw in that example. Here's how you can define your own custom functions. So you do f bracket x underscore comma y underscore. That tells Mathematica that these are the variables of our function. And then I just wrote it out here, colon equals that. Okay. Now, if you remember from, oh geez, I forget which section it was. In a previous section, we talked about how D is the the differential operator in Mathematica. So here I'm asking Mathematica to differentiate our function f of x comma y, and then this part tells it to differentiate with respect to x. So actually, let me, hold on one sec. Let me comment, what is it? Geez, I forget what it is. What's the command? Oh my gosh. I forget the comment out command. Is it? Oh, there it is. Wrong. Oh yeah. There we go. So I'm just going to comment that out for a minute. Now I'm going to hit Shift Return. Wait, let me comment these out too. Oops. And let's just look at the derivative. So Shift Return, there it is. That's the derivative that we calculated for derivative with respect to x, right? Let me show you again on the slides so we can verify. There it is. So this is what we had. Oops, this is what we had through our calculation. And this is what Mathematica told us is the answer. So they are the same. Okay, now we wanted to evaluate this at the point 2 comma 1, right? So that's it. That's actually what this line is. Let me uncomment it. And so what I'm asking Mathematica to do is replace all instances in this function with these values right here. So replace x with 2, replace y with 1. Oh, remember to get an arrow, you just do a hyphen and then arrow, or hyphen and greater than sign, and it'll become an arrow. There we go. So this is the function we just computed. This is the derivative, partial derivative with respect to x. I want to replace all instances of x and y in this formula with 2 for x and 1 for y. And we get 100, which is exactly what we computed a moment ago on the slides. There we go. So Mathematica is doing it too. Then now let's do the same thing, but let's do the derivative with respect to y. So let me uncomment this and recompile. There we go. Now we have it all together. So here is the partial derivative of f with respect to y, and here's what you get when you evaluate it at the point 2 comma 1. And that's pretty much it. Not too bad, huh? All right, so now let's get back to the slides. We did that. Okay, perfect. So here's one that I want you to try on your own, and then we'll do it together. So let f of x comma y be equal to this function. I want you to find the partial with respect to x at 1, 1, the partial with respect to y at 1, 1, and then, using some techniques you remember from earlier sections, I want you to find the equations of the corresponding tangent lines at that point. This is the z coordinate of the point. If you plug in 1, 1 to your function, you'll get the number 1 out. So try this one on your own, but first, just think about how you would approach it. Right? Now say something out loud about how you would start it. Remember, you don't have to say this to anybody. You can say it to yourself, to your dog, to your cat, to the wall, just something to give your brain that verbal feedback. Right. Now try to calculate it on your own. And remember, you are finding the equations of the tangent lines. So don't forget to find the actual equations of the line, not just the slopes. All right, now let's do it together. So first thing we got to do is compute both partial derivatives and then evaluate them at 1 comma 1. So to compute f sub x, we treat x as a variable and treat y as a constant. And we get this. Oh, sorry. Wait, what am I saying here? Oh, I see. I see. I see. I wanted to give another geometric picture of what's going on here. So let me flash forward and we'll come back to this. So here are the partials. If you differentiate z with respect to x, you're going to get negative 2x. So we'll say z is f of x comma y. Differentiate with respect to x, this goes to 0, this goes to 0, this becomes negative 2x, boom. Evaluated at 1, 1, we get negative 2. Next, do the partial derivative with respect to y. So this becomes 0, this becomes 0, this becomes negative 4y, boom. Evaluated at 1, 1, you get -4. So what we just found was the slopes of the tangent lines in the x and the y directions, respectively. Now let me go back to that picture. So the graph of this thing is actually a paraboloid. So this is what the surface looks like here, part of it at least. And then if we set y equal to 1, we're slicing the parabola with this plane right here. And then what you get is you get a curve, the curve of intersection of those two surfaces, right? The paraboloid and the plane. And this is the curve. Now, we just found the slope of this tangent line to be, what was it, -2? Yeah, -2. So the slope of this line is -2. Similarly, for the derivative with respect to y, we held x fixed at 1. So that's like slicing it like so. Oops, wait. There you go. Slicing it like so, and then you get this curve. And we found the slope of this tangent line at this point was -4, right? Yeah, -4. So that's what we just computed. That's what those are right there if you want to see a picture of what's going on. Slopes in the x and y direction. Now, we don't want to dust our hands off yet. It did say to find the equations of the corresponding tangent lines. But if you remember, if we've got a slope and we've got a point, we might as well use point slope form and we're done. Yeah, point slope form. It's that same. Oh, wait. Hold on. What am I doing here? Oh, yeah. Sorry. Getting ahead of myself. Um, yeah, getting ahead of myself. I apologize. So let me back up a minute. Look at these slopes. So this is the slope of the tangent line in the x direction, right? So we can write this as a slope, or sorry, write the slope as a vector in this way. So literally rise over run, right? Rise over run. But the run in this case is, wait, hold on. Give me a second here. Let me pause this. All right, okay. So let me, geez, hold on a second here. Yeah. Okay. So I do have an error here. I knew something was kind of off when I said it out loud to myself. This is why you want to do verbal feedback, right? Give yourself that verbal feedback. So let me explain what's going on here. This is the slope in the x direction, but this is another reason why it's helpful to think of this as partial z, partial x. So what I've done here is I've actually mixed up the rise and the run on the slides. So I'll fix this after the recording here. But these two should be switched. So the rise is -2 and the run is 1. So really what these should be are these. I'm actually going to do the correction right here. This should be 1, comma 0, comma -2. And the same thing for this one. I switched the rise and the run. So this should actually be 0, comma 1, comma -4. So same thing here. Basically replace this with this at every instance. So I do apologize. I'll fix this on the slides as soon as I'm done here. And then that will actually change these as well. So this should now be, okay, this is going to become, well, 1, comma 1, comma 1 stays the same. But now we're going to get, let's see. Oop, wait. I'm mixing myself up here. No, don't mix up. Move this right up there. Move this right up there. Okay, let's try this again. So this will now be equal to 1 plus t, comma, 1, comma, 1 minus 2t. So just a little switch. And then this one, maybe I'll move this down here so it doesn't get as confused. 1, comma 1, comma 1 plus t. So then we have 1, comma 1 plus t, comma 1 minus 4t. There we go. That's the idea. One thing I was going to add is that this vector here, 1, comma 1, comma 1, that's the position vector of the point. The position vector of the point. All right, so I apologize about those errors. I will fix those after the recording. Okay, next example. This is one that I want you to try on your own, actually. So you got to kind of dig back into your memory of implicit differentiation from Calc 1. And I want you to try to do this one implicitly. So find partial z, partial x, and partial z, partial y. If we know that z is implicitly defined as a function of x and y, and it's given by, and this is the equation that describes the relationship. So think about this one for a minute, right? Now say something out loud to yourself about how you would proceed. And now try to work it out on your own. Just as a little hint, remember implicit differentiation really is just the chain rule in disguise. Right, here we go. So if you remember from Calc 1, you're basically going to differentiate both sides of this equation with respect to x. We'll do partial z partial x first. And because we're assuming that z is implicitly a function of x and y, when we differentiate the z expressions, we're going to have to use the chain rule. So here's what we get. Differentiate both sides with respect to x. We're going to treat y as a constant here. So the y is going to disappear if it's all on its own. X cubed with respect to x becomes 3x squared. Y cubed doesn't involve x, so it's 0. Here's where we need to use the chain rule. So we're going to get 3z squared times the derivative of z with respect to x. That's the chain rule. Then this we're going to have to use the product rule on, so be sure to walk carefully with this calculation. You should get 6yz plus 6xy times partial z partial x, and then differentiate 1, it becomes 0. Now what we can do is we can combine like terms, so get all the terms with partial z partial x together and move everything else to the other side. And then you can factor out partial z partial x and then solve for it. And we've got that right here. So this is the final answer, partial z partial x. Right. Now, you can try to do partial z partial y. I won't do the full calculation, but what I do want to show you is how to do this in Mathematica. So, of course, Mathematica can also do implicit differentiation. Let me pull it up right here. So maybe this is a, yeah, here. Just to not spoil it so quickly, let me comment out this line. I guess I don't need to actually like highlight it, but let me comment out this line. Let's verify that we did our implicit differentiation correctly. So the command that Mathematica uses is implicit D, so implicit differentiation, and you give it an equation. Here's the equation we started with. And then you tell it basically what are the derivatives going to be. So we're saying that z is an implicitly defined function of x and y, right? But we want the derivative with respect to x. So we're saying that z is implicitly defined as a function of x and y. So shift return, boom, there's the result right there. And that is actually what we computed. Let me flash back. There it is. All right. Now, for those of you that did already try to compute partial z partial y, let's check to see if you were right. So let me uncomment this line, recompile, and there is the derivative with the partial derivative of z with respect to y, assuming that z is defined implicitly as a function of x and y. All right, cool stuff. Okay, let's go back to the slides here. Move that out of the way. Yes, so naturally, there's like a running theme in this course, right? Naturally, all of this can be extended to any number of variables. So this doesn't just have to work with 2 variable functions. These can be functions of any number of variables, 3, 4, 5, n. So how does the definition change? Well, it changes as you would naturally expect. So if we have a function f that's a function of n variables, meaning that it takes n inputs, or it takes in a point with n coordinates, or a vector with n components, then its partial derivative with respect to the ith variable is the same thing that we saw before, except now the increment is only in the ith direction. So here's the first point, or the first coordinate, dot, 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 I minus 1th coordinate, ith coordinate, and that's where the increment lies. I plus 1th coordinate, dot, 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 nth coordinate. So it is literally just the difference quotient again. It's the difference quotient. And now we're taking the partial with respect to x sub I, the ith component or the ith coordinate. All right, so this is a good time for you to try this. here is a function of three variables. The function is e to the xy times log z. And I want you to try to do these ones on your own. Try to compute partial x, partial y, and partial z, right? So just like before, think about how you would begin. Say something out loud to give your brain that verbal feedback so you don't make a catastrophic error. And now try to work them out on your own. Okay, here we go. So the process is the same. If we want to differentiate with respect to x, x is the only variable involved. So this becomes this. If we want to differentiate with respect to y, y is the only variable involved. So that becomes this. And that's just using the chain rule, actually. If we want to differentiate with respect to z, we get this. So those are the three partial derivatives. All right, so next, naturally we can talk about higher derivatives. So you might remember from Calc 1, you would do a first derivative, second, third, and there were as many derivatives as you wanted. Same thing still applies here. The trick now, or the issue now, is that you can do all sorts of mixed partial derivatives. You can do all sorts of combinations of things, right? So again, remember, think about what we're doing. If you differentiate with respect to x, you're getting a function that gives you the slope in the x direction, right? But that function might still have multiple variables in it. It might be a function of multiple variables. And then you can then take that function and differentiate it again, and you have to choose the direction, right? You have to choose the direction that you're going to be differentiating in. So if we wanted to do the second partial of f, we can do f sub x and then differentiate with respect to x again. That's equal to f sub xx. We're going to see this again in a few minutes, or f sub 1, 1, taking the partial with respect to x and differentiating it with respect to x again. This notation, there's a lot of equivalent notations. Now, where things get interesting is we don't have to take the derivative in the same direction each time. So we can do a partial with respect to x and then do it with respect to y. And again, this is why Leibniz notation is a little bit better. So Leibniz notation, or this notation here, which, oh geez, was this, oh man, I forget who came up with this notation. Darn, I can't remember. Um, the main idea is if you want to have all these different derivatives, you need to indicate the variable of differentiation. So you got to like forget about prime. Can't really do prime anymore. You got to do something that says what the variable is. We could do differentiate with respect to y and then x, or y and then y. And then if you had a function of n variables, you can imagine. Just keep going. Just keep going. All right. So here's what I want you to do. I do want you to try this one on your own first. I want you to find all of the second partial derivatives of this function. So there's going to be a few, right? You're going to have to do the second partials with respect to x and respect to y. So you should have a few results. First, think about how you would start. Right? Now say something out loud to yourself. Right? And try to work it out. Okay, now let's do it together. We're going to have a few. So first of all, the partial with respect to x is this. Remember, you can also use Mathematica or Wolfram Alpha to verify that you did it correctly. Here we get the partial with respect to y. Now we have those first partials. We're going to get we're going to get two other partial derivatives after that, since we're doing the second partial derivatives. We're going to take f sub x and differentiate with respect to x. And we're going to take f sub x and differentiate with respect to y. And then the same thing here and here. So we take this and differentiate with respect to x again to get this. And then to get this down here, we take f sub x and differentiate with respect to y. And we perform the same kind of operation over here. So take this, differentiate with respect to y, take this, differentiate with respect to x. And then what I want you to do, excuse me, is notice that these mixed partial derivatives, these mixed second partial derivatives are equal. They're actually equal. Notice that? Well, that's not a coincidence. That's not a coincidence, and that's actually characterized by the following theorem, which is Clairaut's theorem. So here's the theorem. It says, suppose f is defined on a disk D that contains the point a comma b. If the functions f sub xy and f sub yx are both continuous, then it must be the case that they are equal. It must be the case they are equal. So that's an interesting result. This is one I want you to just kind of ponder for a minute. Yeah, so if those second derivatives, those second mixed partials are continuous, then they are equal. Yeah, all right. Interesting result. And then again, you can do higher partial derivatives. So you can actually use this theorem again to show that these third order derivatives are going to be equal. F sub xy, f sub yxy, f sub yyx. Those are also going to be, if those functions are continuous, they will also be equal. Okay. All right, now we get to do a slight tangent. We won't spend a ton of time on this, but now you actually have a bit of the language to discuss partial differential equations, or PDEs. Um, in Calc 2, you actually saw examples of ordinary differential equations. Those are called ODEs, and there's a whole class on that. So you might even take it here at SMC, ODEs. I know at least a couple of you are taking it right now as well. So that's a whole class on how to solve differential equations, ordinary differential equations. But things get a lot more interesting when you start talking about PDEs. So it turns out that a lot of phenomenon or a lot of phenomena that you observe in the world can actually be described through a PDE. ODEs aren't quite sufficient. ODEs can work, but PDEs are where it's at. So what is a PDE? A PDE is an equation that relates an unknown function and its partial derivatives. And usually the goal with a PDE is you will find some relationship that relates partial derivatives and a function, but you don't know what the function is. You just know how the derivatives and the function are interrelated. And then the goal is to solve that PDE and recover what the actual function is. That's the goal. So we're going to look at just a couple PDEs, and these are ones that you want to keep an eye out for. One of them is Laplace's equation. It's one of the most important ones. Uh, the other thing about PDEs, again, they extend to any number of dimensions. So in 2 dimensions, Laplace's equation is this. So what this is really saying is that if you have a function u of 2 variables x and y, then uxx plus uyy is equal to 0, equal to 0. So this is Laplace's equation. And the solution to this equation, the functions, remember there could be many functions that are solutions. These are actually what we call harmonic functions. So solutions to this PDE are called harmonic functions. They play a central role in heat conduction, fluid flow, electric potential, just analysis in general. Harmonic functions they just show up everywhere. We will actually see them again in chapter 16. Uh, I'm going to show you my PDE book in just a moment here, but I wanted to show you the n-dimensional version of this. So the n-dimensional version of Laplace's equation is this. What are we really doing? We're just adding up all of the second partial derivatives, x, x, y, y, z, z, t, t. We're just adding them all up and setting it equal to 0. So that's what this is saying here. All right. Now, I wanted to show you this. So for any of you that are really, really interested in like fluid dynamics, aerodynamics, you want to start to think about PDEs. So what I wanted to do is actually show you this here. So this is kind of like the Bible of PDEs. Oops, sorry. There you go. Yeah, partial differential equations, Lorentz Evans. So I recommend for those of you that really want to go into like fluid dynamics and aerodynamics, find this book. It's not too expensive, but this is like the Bible. It is extremely dense. There is so much stuff in here. But I wanted to show you at least this page right here. Here you go. Page 20. Okay, there it is. Oh, wait. Give me a sec. Come here. There we go. Okay. Come on. There you go, Laplace's equation. And there it is right at the top. There's that fancy symbol, that triangle. it doesn't really mean delta. It just becomes a shorthand when you're talking about this particular equation in higher dimensions. There's another version of it called Poisson's equation, and that basically means that when you add up all those non-mixed second partials, it actually is equal to a function. There it is right there. Um, let's see, this one, oh yeah, so this is, here you go, this part too. Right, right, right. Okay, there we go. Come on, you can do it. Come on, camera, there we go. So if you're interested in studying chemical concentration or temperature or electrostatic potential, then this equation starts talking about the law of diffusion, the law of heat conduction, and Ohm's law of electrical conduction. So that's where this kind of stuff comes into play, just to give you an idea. All right, now, let's see. Okay, let's get back to these. Oh, let me turn this off. Nice. All right, so let's try to do this one. And this is one I actually want you to try on your own. You can do this. So here, I want you to show that this function is a solution of Laplace's equation. All right, so I'm telling you what the function is. Just show that it satisfies Laplace's equation, okay? So we'll just jump right to this. Say out loud what you think you would try first. Right, now try to work it out on your own, and then we'll do it together in a moment. Okay, so since we are being told that it is a solution to Laplace's equation, that means that if we find the non-mixed second partials with respect to x and y and add them up, we should get 0. Let's see if that works. Here's the partial with respect to x. Here's the second partial with respect to x, unmixed. Partial with respect to y, second partial with respect to y, unmixed. And if we add this to this, we do indeed get 0, as you can tell. This and this are opposites. That's another way of thinking, that's another way of interpreting this equation. It's saying if there's only two variables, right? It's saying that these two have to be opposites of each other. And that's it. All right, another very important PDE is the wave equation. So quite literally, this equation describes the motion of a waveform. So if you've ever imagined waves of any kind and you were wondering like how to describe them, this thing actually encapsulates them. So this one, again, is a little bit different, but it is a PDE. Oh, shoot, I forgot my equal sign here. Another typo, 0. Yep, that's 0. Yeah, yeah. This one is basically saying if you do two derivatives with respect to time and two derivatives with respect to position, and then this is a little scaling coefficient that has to do with like the density of the thing you're working with, then these should be opposites, or when you do this difference, you should get 0. So that's the wave equation. And naturally, I think that one was just a couple pages further. If that's the heat equation. Heat equation is another important one. Where is it? Yeah, so look, check out this. I'll show you. Just a little bit further along in this book. Oh, gotta do this too, sorry. There you go. Right here. There it is. So it's the same thing. It's just using that fancy symbol for the the frankly like the Laplacian. That's really what it's doing. So this is kind of related to the Laplacian. And the reason that they don't have that A in there, they do have it later on. So if you look down at the bottom, right here, give it a second. There it is. There you go. So it says for small du, the linearization is often appropriate. And so the formula becomes that. And it's the wave equation that they call when A is equal to 1. So it's the same kind of thing, right? Linearizations are something we'll talk about in a couple more sections. All right, so now, looks like my camera is crapping out on me a little bit here. Okay, so same kind of question here. I want you to try this one on your own. I want you to verify that this function satisfies the wave equation. So again, I'm telling you the function is a solution. Show that it's a solution by computing those second partial derivatives and adding the results and seeing if you get 0. All right, This one I'll just skip right to the writer. Just try to work it out on your own, and then we'll do it together. All right, here we go. So we need to compute some second partials. Partial with respect to x, second partial with respect to x, partial with respect to t, second partial with respect to t. And here you're just using the chain rule like you normally would from Calc 1. And then we need to show that this difference is 0. Well, when you put these things into it, or maybe you can, well, they're not quite opposites. Excuse me, they're like scaled opposites. But this plus this is definitely equal to 0, so it is a solution to it. All right? Okay, and on that note, let's play. So that's a good place to pause right there. Let's see, did I have any more Mathematica stuff? No, that's it. That's it. You can mess around with Mathematica more if you're interested. But I'll go ahead and stop there. I won't ramble for too much longer. If you got questions, ask when we're in class. Otherwise, I'll see you next time.